The Secret History of Leaded Gasoline. On August 30, 2021, leaded gasoline was officially abolished worldwide. Yet the consequences it left behind are still present. For nearly a century, billions of people unknowingly inhaled toxic fumes produced by leaded gasoline. This toxic substance led to a decline in intelligence, accelerated the development of cancer, and increased the risk of cardiovascular death by up to 70%. Why did this terrible poison come into existence? And what caused us to spend hundreds of years trying to get rid of it? This is Claire Patterson, one of the most talented geochemists in the United States in the last century. In 1944, Claire was invited to participate in humanity's first nuclear weapon development program, the Manhattan Project, where his task was to process uranium by separating uranium-235 from uranium-238 using a device called a mass spectrometer. This device can classify the isotopes within the same substance. If you don't know, isotopes are atoms of the same chemical element that have the same number of protons but differ in the number of neutrons in the nucleus. For example, every uranium atom has 92 protons and 92 electrons. But uranium-235 contains 143 neutrons, while uranium-238 has 3 more neutrons. And the mass spectrometer is sensitive enough to detect that very small difference. When the war ended, Patterson continued his PhD studies at the University of Chicago. Here, he still worked with the mass spectrometer. But to solve a greater mystery, how long has the Earth existed? Since the time of Julius Africanus. Around the 3rd century, people believed the planet was only 5.700 years old. By the Age of Enlightenment, the estimate increased to millions, then billions of years. When Patterson began his research, the scientific community believed the Earth was 3.3 billion years old. However, that belief was still surrounded by much controversy. At the University of Chicago, he was guided by Harrison Brown, a nuclear scientist also fascinated by the question of the Earth's age. Brown believed that uranium was the universe's natural clock, because uranium has a very long half-life, and the final product of that process is highly stable lead isotopes. For example, a 1 kilogram block of uranium-235 will take 703 million years for half of it to turn into lead, while a block of uranium-238 will take about 4.5 billion years. If the ratio of these two elements in a random rock sample could be measured, one would know exactly when it was formed. Therefore, calculating the age of the Earth was entirely feasible. However, the rocks on Earth are no longer intact from its early stages. Volcanoes, tectonic plates, and weathering have repeatedly renewed its crust and erased its original state. Therefore, Patterson needed a primordial sample remaining from when the solar system was newly formed. But where to find it? The answer lay in meteorites. They are the fragments left over from the formation of the solar system. Unlike Earth, they did not undergo intense plate tectonics or volcanic activity, so their primitive composition remains relatively intact. When they fall to Earth, they carry a chemical record from the primordial age, helping scientists measure the age. Thus, Patterson chose a meteorite sample recovered from Diablo Canyon near the Arizona meteor crater, and the result determined the age of the Earth to be 4.55 billion years old, a number that is still recognized by the majority of the scientific community. However, a problem arose during the research. The uranium measurement data was quite stable, but the amount of lead was abnormally high, much higher than the amount that could have been produced solely from uranium decay in the sample. Initially, Patterson suspected the error came from unclean instruments. But even after cleaning everything and using pure distilled water, the measurements still showed an excess of lead. Clearly, an unusual amount of lead existed everywhere in the surrounding environment. But where did it come from? To find the answer, we must go back to the early 20th century. In 1908, on a bridge in Detroit, the Motor City of the U.S., a woman was struggling because her Cadillac suddenly stalled. Fortunately, another man saw this and decided to stop and help. At that time, there was no starter button to start the engine. The driver had to manually crank an iron handle at the front of the car. The man quickly bent down, grabbed the handle, and vigorously turned it. The engine immediately roared, but the kickback from the starting process suddenly jerked the crank backward. hitting the man directly in the face. As a result, he was injured in the face and died due to the severity of the wound. That man was Byron Carter, an automobile inventor who founded the Carter car brand. His death left a sense of mourning for the entire nascent industrial world at the time, including Henry Leland, the founder of Cadillac. According to a later biography, Leland wrote, "I regret having built automobiles. But that damned crank. I will not let a Cadillac harm anyone else." Leland was determined to remove that dangerous part from the car. And Charles Kettering, a talented engineer, was assigned the task of inventing a completely new starting system. By 1911, the Cadillac Model 30 was launched and immediately made a big splash, for the first time in history. Starting the car only required one action: turning the key. Not only did it impress with the new starting technology, but the Model 30 also possessed superior power, a 40-horsepower engine, and a top speed of up to 72 kilometers per hour, twice as fast as the Ford Model T, the most popular car at the time. But this model was also not perfect. The sound from its engine was very unpleasant, like a hammer hitting iron. The cause lay in the cylinder part, where the piston constantly moved up and down to compress the mixture of gasoline and air. Normally, when the piston reached its highest point, the spark plug would ignite, detonating the fuel to generate power for the car. But in the Model 30, the excessive compression ratio caused the mixture to auto-ignite prematurely before the spark plug fired. The result was that instead of smooth, rhythmic explosions, the cylinder was rattled by random, chaotic explosions. The impact pressure went straight to the metal wall, creating that heavy noise. Engineers called this phenomenon engine knocking. It not only created an unpleasant noise but also wasted fuel. Furthermore, the continuous impacts caused the piston to shake violently, the cylinder wall to wear down, and the engine to quickly fail. But there was a way to eliminate this annoyance, and the most effective way was to change the fuel. Each fuel type has a different compression resistance before auto-igniting. For example, a compound called N-heptane is extremely flammable. When lightly compressed in an engine, it almost immediately detonates, causing a knocking sound. Meanwhile, isooctane is much more stable. It can withstand high pressure in the cylinder without spontaneously igniting, allowing the engine to run more smoothly. To measure the tendency for early or late ignition, scientists developed the octane rating system, in which isooctane is conventionally set at 100, and N-heptane is 0. In reality, gasoline does not only contain these two compounds but is a complex mixture of dozens of different substances. But for simplification, scientists use isooctane and N-heptane as the standard measure. Thus, the octane rating of a type of gasoline indicates how many percent of isooctane is mixed with how many percent of N-heptane. For instance, a 95 gasoline is considered to have 95% isooctane and 5% N-heptane. In the early 20th century, the gasoline sold on the market often had a low octane rating, leading to premature ignition and the engine knocking phenomenon. Charles Kettering wanted to find an additive that could raise the octane rating of gasoline. To make the idea a reality, he sought out Thomas Midgley, a talented young engineer. Midgley started testing all kinds of compounds, from melted butter, mothballs, to ethyl acetate, a compound that creates artificial fruit flavor, and aluminum chloride. However, most did not yield the desired effect. Only ethanol offered some hope. This alcohol prevented the annoying knocking sound in the engine, but it required mixing 10% of it into the gasoline to be effective. And that ratio was too costly and could not generate a profit. Midgley needed a solution that was cheap, simple to manufacture, and required only a very small amount but still worked. He switched to trying tellurium, a rare element, but it had a horrible, persistent smell that couldn't be washed off even after bathing or washing clothes. Therefore, this element was also eliminated. On December 3, 1921, after half a decade of struggle in the lab, Midgley finally found the answer: tetraethyl lead. After adding this heavy metal compound to gasoline, the engine knocking phenomenon completely disappeared. Moreover, it was odorless, low cost, had abundant supply, and was suitable for industrial production. Immediately after, Midgley and Kettering rushed to register the patent. They cleverly named the product ethyl to make people easily confuse it with ethyl alcohol. an industrial alcohol, and most importantly, to avoid mentioning the word lead, which evokes a sense of insecurity. Soon after, they partnered with three giants in the U.S. economy to establish the Ethyl Corporation. A massive advertising campaign was launched, hailing this new fuel as a scientific breakthrough that ushered humanity into an era of convenience and prosperity. The most notable event occurred in 1923, when the top three racers in the Indianapolis 500, America's prestigious car race, all used ethyl-leaded gasoline. Fuel efficiency immediately soared, and demand increased rapidly. To meet the market demand, the Ethyl Company built a new chemical plant in New Jersey. But that ambitious start quickly turned into a tragedy. Just a few months after operation at the New Jersey plant, dozens of workers fell into a state of panic, convulsions, and screaming like madmen. The New York Times headlined, "Strange Gas Kills 4. Drives 1 Mad. Injures Workers at Standards Lab in Elizabeth, NJ." Within a week, hospitals in the area admitted an additional 36 patients with similar symptoms. And at least 5 people died in just 2 months. Leading experts on toxicology and exhaust fumes continuously issued warnings, calling tetraethyl lead a silent killer. The risk of poisoning was not limited to factory workers but could spread to millions of people inhaling car fumes across cities. To reassure the public, Midgley held a press conference on October 30, 1924, in front of the cameras. He calmly poured the tetraethyl lead solution onto his bare hand, then brought it close to his nose and inhaled deeply for a minute. Afterward, he smiled and said, "I can do this every day without any ill effects." The press immediately reported on the safety of ethyl. But the truth was completely different. Midgley knew well the danger of tetraethyl lead. But how dangerous was it really? Lead is an extremely toxic substance, even in very small amounts. After entering the body, lead mimics calcium, rendering the natural detoxification system powerless. It accumulates in the bones for a long time and causes harm years after the first exposure. The part that suffers the most severe damage is the brain. This metal destroys myelin, the sheath surrounding nerve fibers, blocking signal transmission. Consequently, people with lead poisoning often suffer from headaches, memory loss, and numb limbs. In fact, humans had known about the harmful effects of this heavy metal since ancient times. Vitruvius, the famous Roman architect, left a warning in his work. Water from clay pipes is much safer than from lead pipes. Water seems to become poisonous when flowing through lead. Despite this, the truth was suppressed. The Ethyl Corporation hired scientists to argue that lead was a natural component of the environment and therefore not a concern. The president of Standard Oil, Frank Howard, even boldly declared, "We cannot refuse a gift from heaven just because it has the potential to cause harm." As a result, that toxic lead existed for the next 40 years. It wasn't until Claire Patterson began his research on the age of the Earth that the truth gradually came to light. And since then, the journey to expose one of the biggest environmental crimes of the 20th century began. To find the answer to the widespread lead pollution, Patterson turned to the place that could record the planet's history over millions of years. And nowhere was more suitable than the ocean. His idea was simple. If the lead in seawater were entirely natural, the concentration would be uniform at all depths. But if it was discharged by humans, the surface layer would surely be much denser than the deep bottom layer. The results showed that the amount of lead on the sea surface was 10 times higher than at the bottom. Patterson decided to review documents to find the cause of this unusual phenomenon. In the process, he accidentally came across data on the leaded gasoline commonly used at the time. When cross-referencing, Patterson discovered that the amount of lead in the seawater matched the estimated amount of lead that cars had released into the atmosphere. That correlation led to a single conclusion: the source of pollution is not natural, it comes directly from the oil industry. Patterson understood that these large corporations had funded his lab. Publishing the research results meant directly confronting the strongest financial powers in the U.S. But as a scientist, he still chose to speak out. Right after his article in the journal Nature,